Hi, class. Welcome to the second part of today's lecture. So right now we're going to talk about the setup for the early chemistry of the Earth's atmosphere. This is what is going to set the stage for the very first development of life on Earth, and ultimately what's going to lead to the more complex forms of life that we see today. So in the last part of the lecture, we talked about the early Earth itself, where it came from, how it condensed, and how it formed. And now we're going to talk about how the volatiles that we talked about and the early environment of the Earth transformed itself. So ultimately it became like what we see back there, a planet that certainly has plenty of liquid water and an atmosphere that life forms can exploit for their lifey purposes. Okay, so those are kind of the defining features that we think are involved in this. So let me start on a few slides here. Okay. So the hydrosphere that we discussed last time is really all the air and the water on Earth. It is by and large largely confined to the surface. There is obviously subterranean air and subterranean water and water at the great depths of the ocean and whatnot. But that's to be distinguished from what we normally call the lithosphere, which is the solid body of the planet. Okay, so we're just talking about the volatiles that are above it. So we'll just talk a little bit about the composition of the early atmosphere. We'll talk a little bit about what drives the evolution of the atmosphere and how it changed. We'll come back to that after we talk about the very first life forms, because life had a very dramatic impact on the evolution of life here on the planet. And then lastly, I want to talk about the Miller-Urey experiment, which some of you may know about. The Miller-Urey experiment is a very famous experiment about the development of the building blocks of the chemicals that eventually are used in the life processes. Okay? So atmospheric players, when we talk about the development of the atmosphere on Earth, is kind of threefold. So there is the production of gases itself. Where did the gases in the early atmosphere come from? When the planets first condensed out of the protosolar nebula, we really just think of them as being rocks. Certainly as their gravity grows, they can hold on to an atmosphere, and so they might necessarily condense atmosphere out of the protosolar nebula. But by and large, as they're growing and when they're small, like Mercury or the moon, they don't have any atmospheres at all. And so largely we think that the production of most of what you and I would call the atmosphere is created by geology. We'll talk about that, and by the volatile delivery that we discovered last time. Photochemistry, the interaction of the protean atmosphere with light, with energy from the sun, plays a very important role in the evolution of the atmosphere and how the atmosphere changes over time. That is still true today. Those of you who know a little bit about atmospheric chemistry will remember that the ozone layer, which is above our heads, absorbs ultraviolet light. That's what protects us, and that's why the ozone hole is such a big deal. The way it does that is the ultraviolet light is absorbed by ozone, which breaks it into smaller components of oxygen. Okay, so photochemistry is still playing a role today in the Earth's atmosphere, but it was particularly important in the early atmosphere for driving changes that led to the atmosphere that we enjoy today. And then lastly, there's hydrosphere interactions. And so this is chemistry with water. There's lots of hydrochemistry that goes on that's also involved in the geologic processes. Certainly the atmosphere plus water plus geology changes the structure of the environment over time. And weather in particular is important, because once weather starts on the surface, the cycle of water moving around the planet also moves materials around and mixes them and affects the chemistry around the planet. Okay, now I will mention, and we won't talk about this much, but this is still an area of active research on many fronts. In terms of the proto-Earth, there is still a lot of research being done about what is the actual atmospheric content of the early Earth. And we think we understand a lot of it. We have done a lot of research and a lot of experiments that agree well with observations we already have. But by and large, we still would like ways to directly measure what the early atmosphere was like. So can we dig into the oldest rocks and study their chemistry and find markers that would tell us something about the early atmosphere? Those are the sorts of things that are still going on. There's still also a lot of work into how all of the different parts of the Earth's atmosphere interact. So geology, water, air, chemicals in the air itself. Those are all absolutely forefront areas of research right now. And those concerns and those problems are being driven largely by our current concern with the Earth's climate. And so lots of the chemistry of this is still being studied. And we'll talk about that a little bit late in the quarter when we talk a little bit about climate change. Okay? Okay. So the very early Earth during the bombardment was heavily volcanic. I mean, everywhere on Earth was volcanic. It was active because volcanoes were bursting up. The crust itself had been pummeled. It was very hot. It was melting, right? Everywhere for probably 1 billion years or so after the formation of the Earth. Now, volcanism is volcanism, so the activity that we see and measure in volcanoes today is very similar to the expected volcanic activity that we saw then. The geology and the chemistry of melting rocks and cooling them and having them interact with other melting rocks is largely the same and hasn't changed over geologic time. And so if you look at the signatures in the rocks from billions of years ago, you look at what volcanoes do today, there is a long chain of very typical gases that are produced with volcanic activity. Okay, so water certainly in hydrated minerals is released when this happens. SO2 is silicon dioxide, carbon monoxide, carbon dioxide, not silicon, sulfur dioxide. SO2 is, S is sulfur, S2 is sulfur, chlorine, nitrogen, hydrogen, NH3 is ammonia, CH4 is methane, okay? So these are all chemicals that are produced during volcanic activity. They have great influence on the overall environment, particularly on the atmospheric chemistry. Many of these materials, like sulfur dioxide, when it mixes with water, makes sulfuric acid. Similarly with chlorine. So it has definite effect on the overall atmosphere, okay? But by and large, we think the early atmosphere was really dominated by CO2. There's very little oxygen at this time. Lots of it gets used up in geology. But by and large, there hasn't been a lot of oxygen produced. That's actually something that happened with the advent of life, and we'll talk about that a little bit. Okay, now when the Earth's really hot, there is no liquid water. Okay, so any water that appears here is either bound up in materials or it's water vapor. But as the Earth cools, ultimately all of the water, the volatile water that was delivered by comet bombardments in particular, for instance, would slowly condense out and ultimately will become liquid water. But in the earliest days of the Earth, there was no liquid water around at all. Okay. Now, we said photochemistry is a big part of this. So ozone had not formed. There wasn't very much oxygen around, as we've said, okay? And you need atomic oxygen and molecular oxygen to form ozone. So the ultraviolet light from the sun was penetrating all the way down to the surface of the Earth, and it plays a very important role in driving the chemistry of the atmosphere. Okay, so in particular, the photochemistry of ammonia, NH3, and the photochemistry of methane, CH4, is important because when ultraviolet light breaks up these two compounds, it leaves behind building blocks that can be used then to build the components of what we call organic molecules, which eventually lead to the building blocks of nucleic acids and proteins, what we call amino acids. Okay, so this photochemistry we think was very important early on for providing the chemical building blocks, the chemical environment that we think needed to be around for the early building blocks of life forms to actually be created. Okay, in particular, UV light also breaks up water. That provides hydrogen. Hydrogen is very light. It floats, right? And so it would drift up to the top of the atmosphere, and lots of that hydrogen was lost to space. The oxygen that's left behind is used in geologic processes and ultimately would be used in making ozone, which would slowly taper off the ultraviolet chemistry that we see here on the surface of the Earth. That's why you and I aren't dead yet. Okay? Okay. Now, the big change to the Earth's atmosphere, as far as you and I are concerned, happened not in this early phase. Certainly, the early phases was important because we were providing all the building blocks in the soup that ultimately would become the building blocks of life. But the big change that happened that made life forms like you and me possible is about 2.7 billion years ago, cyanobacteria formed. So cyanobacteria is what's usually called like blue-green algae. Okay. And what cyanobacteria does is it consumed CO2. It uses CO2. It takes the carbon from the CO2, uses that as one of the raw materials to build its processes in its cellular machinery, and then it releases O2, oxygen, as a byproduct. Okay, and that's the same thing that plants do today when they photosynthesize. They take energy from the sun, they take CO2 from the atmosphere, they go through the photosynthesis process to bind carbon and produce energy, and then they release oxygen as a byproduct. Okay, and so what that did is it changed the chemistry of the Earth's atmosphere. Suddenly, oxygen was plentiful. Okay, well, eventually it became plentiful, but it started appearing in the atmosphere. And so over the next 1.5 billion years or so, this caused a great strife within the life that evolved on the planet. In particular, because up to that point, much of life on the planet was what we say anaerobic. It's life that thrives in an environment where there isn't very much oxygen. But because there was plentiful oxygen after the cyanobacteria started making it, then it became possible for life that could thrive around oxygen, what we call aerobic life forms like you and I, life forms that could use the oxygen in their life processes could thrive. Okay, and so you see this kind of bifurcation and this competition between life forms happening after the formation of oxygen in the Earth's atmosphere. And we'll come back to that when we talk about the development and evolution of life next class period. Okay? Okay, so what makes us think all of this this chemistry was going on in the early atmosphere? So there certainly is geologic evidence. As we said, we're going back into the rocks. We can look for those signatures in the rocks. If we go back in the fossil record of life, which we'll talk about next class period, we see the chemical evidence of what the life was doing, which tells us something about the environment it was thriving in. But we've also managed to do experiments in the laboratory, which when we try and simulate different ideas we have about the early atmosphere, and we look at how those experiments evolve, we see them evolving towards the kinds of environments that we think needed to be there to produce life. We see them evolving towards the kinds of environment that we enjoy today. We see them evolving and producing the substructures that we see in the fossil record for life and in the biological record for life. Okay, so the most famous of those experiments was called the Miller-Urey experiment. Okay, so the question that was trying to be answered, so this was carried out in 1952 by Stanley Miller and Harold Urey right here in Chicago at the University of Chicago. The question that people were trying to answer is, where did the raw materials that became life, as you and I call it, come from in the early days of Earth? Okay, and what we mean by that is, where are the raw organic molecules, okay, or in more complicated structures of molecules, where did the amino acids, the building blocks for proteins and the building blocks of nucleic acids come from? Okay, and so what Miller and Urey did is they produced an experiment in the laboratory where they produced a raw environment in terms of gases and temperatures and liquid water that mimicked what we think the early Earth was like. Okay. They then provided an external energy source to that. So the early Earth, when the weather patterns started developing, there was lots of lightning. You could do this experiment with UV light as well. But you basically spark the raw form of the atmosphere. Okay, that energy causes chemical reactions among all the complex molecules, and it makes more complicated molecules. Okay, and so that process of taking fundamental molecules, energetically combining them and cooling them, causes them to condense out, and you can look at what the condensed out molecules are. And what they found is they very successfully were able to produce amino acids, which are the building blocks of nucleic acids and the proteins that we see in life today. Okay, so that is going to be a very important point. We'll come back to this either on Wednesday or Friday, where we talk about whether or not the circumstances that we encountered on Earth that led to life on Earth are unique or not. It is easy to make what we on Earth regard as the fundamental building blocks of all our molecular machinery. Okay? Okay, so Carl Sagan, those of you who know a little bit about science communication and astronomy communication in particular, Carl Sagan wrote a very famous book in the 1980s called Cosmos. There was a very successful PBS show, 13-episode PBS show, which you can still get on DVD. This has been followed up by 2 sequels, one of which is going on right now if you're watching it on National Geographic Channel, another one several years ago. The modern ones are hosted by Neil deGrasse Tyson. But in that first Cosmos series, Sagan had a great segment where he filmed them doing the Miller-Urey experiment in a laboratory at Cornell, where he was a professor. So I'm going to end the lecture here today with a video clip from that episode of Cosmos, so you can see the Miller-Urey experiment in action. Okay, so let's watch that.
Now, how did the molecules of life arise? In a laboratory at Cornell University, we mix together the gases and waters of the primitive Earth, supply some energy, and see if we can make the stuff of life.
And scientists, right?
But what was the early atmosphere made of? Ordinary air? If we start with our present atmosphere, the experiment is a dismal failure. Instead of making proteins and nucleic acids, all we make is smog, a backward step. Why doesn't such an experiment work? Because the air of today contains molecular oxygen. But oxygen is made by plants. It's pretty obvious that there were no plants before the origin of life. We mustn't use oxygen in our experiments because there wasn't any oxygen in the early atmosphere. This is perfectly reasonable because the cosmos is made mostly of hydrogen, which gobbles oxygen up. The Earth's low gravity has allowed most of our original hydrogen gas to trickle away to space. There's almost none left. But 4 billion years ago, our atmosphere was full of hydrogen-rich gases, methane, ammonia, water vapor. These are the gases we should use. Taking great care to ensure the purity of these gases, my colleague Bishan Kari pumps them from their holding flasks. An experiment like this was first performed by Stanley Miller and Harold Urey in the 1950s. The starting gases are now introduced into a large reaction vessel. We could shine ultraviolet light on this mixture, simulating the early sun. But in this experiment, the gases will be sparked, as the primitive atmosphere was by early lightning. After only a few hours, the interior of the reaction vessel becomes streaked with a strange brown pigment, a rich collection of complex organic molecules, including the building blocks of the proteins and the nucleic acids. Under the right conditions, these building blocks assemble themselves into molecules resembling little proteins and little nucleic acids. These nucleic acids can even make identical copies of themselves. In this vessel are the notes of the music of life, although not yet the music itself. Now, no one so far has mixed together the gases and waters of the primitive Earth and at the end of the experiment had something crawl out of the flask. There's still a great deal to be understood about the origin of life, including the origin of the genetic code. But we've only been at such experiments for 30 years. Nature has had a 4 billion year head start. Incidentally, there's nothing in such experiments that's unique to the Earth. The gases we start with, the energy sources we use, are entirely common through the cosmos. So chemical reactions, something like these, must be responsible for the organic matter in interstellar space and the amino acids in the meteorites. Similar chemical reactions must have occurred on a billion other worlds in the Milky Way galaxy. Look how easy it is to make great globs of this stuff. The molecules of life fill the cosmos.
Okay, so you see there, Sagan certainly has the optimism that that there's plenty of life around the cosmos, or at least the opportunities for life. And we'll come back to that discussion at the end of the week. We're going to talk again about the questions, the notions that we started the class with, the principle of mediocrity and the rare earth hypothesis in the context of the kinds of chemistry that we're talking about right now. Okay, so that's all I'm going to say for the day. I hope you're all having a good time. Good luck with everything, and I will talk to you all soon. Okay, bye-bye.